PYNQ. Okay, so first, the PYNQ is available for Mpsoc. Okay, it's not available for purely PCIe accelerator card. For PCIe accelerator card, you use the XRT. That's another framework. Yeah. So for Mpsoc, I would like to explain the basic structure of the Mpsoc. From the name, you know, in the FPGA, there is a SOC portion. For this is the SOC part. Okay. So that the content of the SOC is like the SOC chip you see. Okay. First, it has the processor section. Okay. For the project, the platform we are use the PYNQ Z2. It has two A9 core, and each with its own mass coprocessor, Neon processors. Okay, and with the cache subsistence. Yeah, and the SoC has a lot of IOs. So this car, you got PYNQ2. You have a USB port, you have a Ethernet port, SDI, SD card, and GPIO UR. UR, you can use a UR to communicate with outside, and you have an I2 CSPI, and you have a local memory, the DDR memory. Yeah, I think the DDR memory you have has a 112 megabytes of memory. Okay, yeah. And this SoC part we call the PS section. Means a processor section, and the FPGA part we normally say is the peer section. So the way the PS and peer, PS basically you run for your host program. Okay, so the processor will run the OS drivers and all the software stack on the SoC part of the processor, and the FPGA part is the yellow regions, and the way the communication between the host or PS part and the peer part is through those AXI bus interface, all those AXI interfaces. Okay, there are two types of XI. One is a high performance. Okay, for the high performance, it has a HP port and ACP port. Okay, ACP port is the one that will be doing the cache snooping. Okay, so for whatever data that's possibly in the cache, and you like the data share with the FPGA part, then you have to use the ACP port. Because the other four high performance port does not go through the snooping logic. The access path directly to the memory. So for example, there are some data inside the L1 or L2 cache. Then the data from the PLSI master could get wrong data or out of date data because they directly access the, I don't know why it's keep jump the screen, yeah. Okay. So for the high performance port, you have a 4 slave 64-bit data bus and one ACP port. Okay. Remember, noted here for those ports. Is there a way won't keep jump? Maybe I should set. Should I set only the? Anyone knows that why my hand touch the screen will jump? Okay, probably my hand should not touch the screen. Yeah. Okay, so in here, if you pay attention, the notion S, that means the master, master is the one initiate the transaction. It starts from the peer side, and the PS side is act as a slave, or you can think it's a memory slave. It responding to the master access. Okay, so those ports only the slave ports. Okay, so if you want the processor initiate the transaction to access the peer side kernel function, you have to use the port here. Okay, so that's a general purpose port. Okay, so in here it provides two master port. That means two port that the CPU can initiate the transaction toward to the kernel functions. Okay. Let's say so in here on this side, the right side is the PS side. So we will see you have the high performance port, okay, and you have a general purpose port. There's a high performance port. And on the peer side, that's where your kernel function. Okay, for kernel function, you want to access doing the data movement from the host memory, from the host DDR memory. DDR memory is located on the PS side. Okay, you have two ways. Okay, one is through you run the AXI master or streaming. Okay, so for this two, we exercise that in our Lab2. Okay, so for the general purpose port, which is the PSI processor, want to communicate with the kernel function, you use the general purpose port. Okay, so it maps to the AXI Lite. Okay, so AXI Lite is used for the block protocol. Block level protocol. That means the kernel function, the whole configuration of the kernel function, how to configure them. Then you use the AXI Lite, or if you want to do the small data transfer from the CPU side to the kernel side, you can use the AXI Lite. For example, in Lab1, okay, we have a very simple multiplication. The operand of the multiplication, actually the data is sent from the CPU. Your CPU program the operand to the kernel function. Yeah. So basically, the kernel function communicate with the host through these three interfaces: AXI master or through the string, and the AXI Lite. Okay. And one thing you need to pay attention to is for the AXI stream doesn't have no address information on the AXI stream. Okay. However, to access the DDR memory, you need address. Okay. So in this case, you have to use a DMA IP. This is a DMA IP. Okay. For DMA IP, that you need to specify the starting address, because string is just a FIFO. Okay, it does a sequential access, but no address. So the address will be programmed into the DMA IP and use the DMA IP to generate the address to access the memory. Yeah. For the XI master, the bus protocol, it has the address information. However, its address is specified also through the XI Lite. You need to use a CPU to program the address for the AXI master access. Yeah. So AXI Lite is a very important interface. Yeah. So at this here, okay, just remember for kernel function to access or communicate with the host, it has three ways. One is using AXI master or AXI stream and AXI Lite. And AXI Lite is used for configuration or doing the small amount of data transfer. For volume data transfer, you use the DMA, okay? And either using the AXI master or using the AXI stream. Okay, for AXI stream, you need to use the DMA IP, which provides address for you. Okay, so this page is very important. Yeah, and we also demonstrate everything in the Lab2. Okay, let's talk about the PYNQ framework. So this portion is the PSI. Okay, PSI, you have two ARM A9 running. Okay, and on top, on the processor, you run the OS, Ubuntu OS, and with a driver built in. Okay, and on top of the OS, you have the Ipython kernel. The Ipython kernel provides the API interface for the application program. And in here, it runs the Jupyter web servers so that you can use a remote terminal using the browser to access the PYNQ framework. Okay, so that's the software stack running on the PS side. On the PS side, you develop the kernel functions, which is the overlay here. Okay, and then in order to communicate with host, the PYNQ framework provides a set of the IP. For example, in the previous, okay, for example, for this one, and also for the all the kernel, in order to hook on the AXI interface, which is the boundary between PS and peer, and you need some kind of adapter circuit, adapter IP. Okay, so you need so the PYNQ framework also include those IP, and this IP you cannot randomly use. For example, for this DMA engine, okay, Xilinx provide all different kind of DMA engine, but you cannot choose any kind of a DMA engine. Although you provide the stream interface, it cannot be used because this DMA IP you use has to be consistent with the driver stack built in here. Because the driver and the hardware DMA IP has to go hand in hand. They have its unique way of communication. Okay. So for the PYNQ package you download, it specify a certain type of DMA IP use. Okay. So when you design the kernels and the PYNQ or I should say the VTs framework will generate a set of first you will generate bitstream. Bitstream is the configuration file to program the FPGA chip, and also a set of metadata. Okay, in particular, it's a header file specify how the host program and how the driver or API communicate with your kernel function. Okay, so the HWH file and the certain JSON file, that are the metadata. The metadata will be all those API will be reading will be reading those metadata files so that he knows how to access the kernel functions. Okay, and in the later course, I will explain the mechanism. And also, you will build up the driver code. Okay, the driver basically for every IP or for every kernel function, which is when you develop at the top level kernel function, it has an associate driver file. Okay, the driver is responsible for programming the kernel function. So in the BTS flow, it's not only compile your design into the RTL, they also generate all the metadata file and the driver file so that it can link with the whole PYNQ framework. Yeah. So this will give you a brief idea, okay, how they interface and what's the relationship between the file and the in the PYNQ framework. And in the later slides, I will explain details. Okay, so this bar diagram gives you the whole picture about the PYNQ framework. So on the bottom is the hardware part, is FPGA. So inside the FPGA, you have the overlay, which is your kernel function, and also there's the infrastructure IP. So it's a part of the PYNQ framework. Using the Xilinx IP to compose. As I said, all those PYNQ IP has associated drivers. Okay, so what the driver here is the driver in the Linux kernel. Okay, so for the Fpga Manager, so this driver is used to configure the Fpga. So basically, it's to download the bitstream file. Okay, in the FPGA, okay, the FPGA we use is SRAM based. Okay, there are several types of FPGA. Some is anti-fuse. Okay, some using the flash memory. Okay, either of them that could not do the real-time programming. And the FPGA we use is SRAM based. That means all the function in your design is configured by the SRAM bits. Okay, so when we said you configure the FPGA function or program FPGA function, basically you are loading the bitstream into the FPGA SRAM bits. And the SRAM bits are all scattered in the whole FPGA chip. Yeah. So this Fpga Manager basically just transfer the bitstream file, load from the file, and then streaming in to program the Fpga SRAM bits to configure its functions. So this function does. And that's the system GPIO, because FPGA side has a lot of general purpose IO ports. Like in here, we see there are many general purpose IO port here. Yeah, use the GPIO, and in our lab we don't use that. Yeah, because it's not really related to high-level synthesis. However, it's an important part of FPGA functions. Okay, and this is an interrupt, and in our lab we don't use interrupt because unless you want to do a very low-level control. Since all our lab we are using either PYNQ or XRT using the framework, and the PYNQ and the XRT using the interrupt to really talk with its hardware. And for us, we don't really to manipulate the interrupt because it's such a very low hardware levels. Yeah. So this one we don't use, and this one we don't exercise. Yeah. And this device memory. So that's a MMIO. So this driver is using the XI Lite to configure your kernel function. This is the driver function for this one. And this one is doing the memory allocation and communicate with the DMA IP. Okay, so you can think this driver is responsible for the communication from PS to peer, from PS to peer. And this one is for moving data from PS, from the data movement from the PSI DDR memory to FPGA part. Okay, so for the Linux driver, we really will be using is this part and this part and this part, and it's corresponding. The API is the overlay here, and for the GPIO, no, the device memory, the configuration using the MMIO, that's the Python API, and the X-Link. Okay, so when you develop the Jupyter notebook, the host program is running here, and you don't communicate with the driver directly. Okay, you communicate with the driver, and the driver communicate with its hardware. Okay, and it communicate with the hardware through the API, and the API communicate with the OS drivers. So for the API, you mostly use the overlay. Okay, you use the MMIO, you use the X-Link, and X-Link on top is the DMA. Yeah. So in your Jupyter notebook, the host program, you will import those package and call the method of the function from those API. Use this way to communicate with your hardware. Okay, so do you understand the whole relationship? Okay. Yes. Okay. Any question, Yilin?
Okay. Yes. Good morning, Professor. I have a question that you said we don't use interrupt here, so which means that we use polling to keep polling the FPGA if the hardware has done its work.
Actually, interrupt is used by the framework. Okay. And for example, like the XRT, that's a PYNQ. Okay, the same thing with the XRT. And because if it's an interrupt, if you use the interrupt, imagine, then you have to develop the driver for interrupt, right? And we are developing the high-level host program. Okay, for host program, you really don't deal with the interrupt. Who will use the interrupt, like a driver? Okay, so that's why we only develop the program at this level. We don't see interrupt. For example, if you develop the application program, have you really deal with the interrupt? No. Yeah. So if you develop the hardware driver, then you deal with the interrupt. So what I'm saying is that since we are using this framework, all the interrupt handling and interaction with the hardware is done by the lower driver layer. Okay, so driver will use the interrupt because the interrupt is for hardware interactions. Yeah, like the OS. For let's say one example, like a timer. For OS doing the multitasking. Okay, so it has a hardware timer. So the timer after a certain time, it generate tick, it generate interrupt. and then always capture it, and then it schedule the event. Okay, so that's why I'm saying that we don't really deal with the interrupt. Yeah. Okay.
So can I have
do you understand?
yeah, okay, so so does it mean that the interrupt is not in the software or hardware level, it's in the firmware level?
It's in the firmware level, right? Yeah. For example, for the kernel function you develop, okay, all the kernel method, kernel development, AAHLS, when you develop the kernel, okay, you don't see, it doesn't provide you any mechanism to generate interrupt. Yeah. So the framework, people designed like the DMA, okay, they may generate interrupt. There are basically two ways, as you say, there are two ways to communicate with. One is using the polling, okay, one is using the interrupt. Yeah. So for example, like we using the DMA IP here, and you can instruct the DMA IP say, okay, if a transfer complete, there are two ways to tell me you complete. One is you have a status register that is done. Okay, then the driver read it. That's the polling mode. Okay, or you can tell the DMA that, oh, you raise the interrupt. Yeah, but all these things is so hardware level that it's supposed not to expose to the application level. Yeah. Okay. So that's why in the AAHLS course I didn't talk about the interrupt, and there's no way to use interrupt when you develop the AAHLS. Okay, that's a good question. Yeah. Okay, I hope you have a clear concept of how the driver stack all hook up together. Yeah, and in the later slide, I will explain much more details that how the kernel function interact with the upper host program. Yeah, but remember all these slides. Okay, you have to remember you have a DOS interface, you have a XI mask ASI string, how to connect to the PS. You need to have a picture about this one, and knowing all the driver stacks. Yeah. Okay. At this stage, you may not be clear. In the later slides, that hope you can link them all together. Yeah. It's a very important. If you simply run through the lab, I believe you can run the lab 1, 2, 3 very quick and very easy without running any problems. But you didn't develop the capability if anything go wrong. You don't have a capability to debug it. And you don't have a capability want to try anything new unless you really know the whole framework, how it works. Otherwise, you don't have a direction what I should look into it. Yeah. Okay. So this one give you a very clear how the software and hardware link together. Okay. On this part, this is hardware. As I said, you communicate, PSI communicate with the PLSI through those interfaces. Okay. Yeah, you have the bit string. That's a spatial hardware. You don't see the hardware here because that's a very secret communication scheme. Probably is proprietary to Xilinx. How the bit string get direct to each SRAM bit to program the FPGA. Okay, I believe I don't find much information about. There's some controlling logic here to have a data from the file. You have a bitstream file. in the file system. When you load in the data, load into the memory, how the memory data get into the FPGA and program each SRAM bit. There are certain controlling logic here, and I don't see document on that. I think it's pretty much proprietary, but you don't need to worry about that. You just need to know there's a function call, and then you provide the data memory, and then you will configure. Okay, and you have a GPIO and interrupt, and we don't address these two. So we'll mainly focus on this. Okay, and for the bitstream, as I said, that's this driver handle that, and the GPIO goes through here, and interrupt goes through here. Okay, so in here we have many concerned two driver here, which is CPU as a master. You want to program the FPGA. Okay, configure the FPGA. You go through the general purpose master port here, and then the corresponding driver is this DEV MEN. Okay, and for the DMA transfer from the DDR memory to the FPGA, so you use this driver code here. So there's a very clear mapping between the driver and the actual hardware interface. Okay, so this MIO, there's an API in Ipython. Okay, so there's a MMIO. MMIO is used to access and control the peripheral. This is the kernel function. Yeah. So in the hardware side, use a general purpose port, and then in your kernel function, you specify the interface is XI light, so that you can connect them. Yeah, and there are a few key to access the configuration space. You need to define the base address, starting location, and the length of accessible memory. You can think I provide a region, that's a memory space. Okay, so you have a base address and the length. Okay, you use this address range to access the configuration of this IP. How do you access it? You use the read-write operation. Yeah. So when you call the MMIO, you provide the base address and the address range. So the question is, how do you know this address? How do you know this base address and the range, the size? Okay. So this information going from your IP, the kernel development. Okay, and the kernel, you have the argument. Okay, you call a function. Function, you have an argument A, B, C, for example. Okay, so when you call the function, you have to provide the argument, right? Yeah. The argument is what I mean the configuration. How do you program transfer the ABC? You do the MMIO using the AXI Lite interface to program these registers. Yeah, and these things will be located in the AXI Lite range. Okay, and when you synthesis and go through the VTIS flow, and this information will appear in the block design, and then there is in the later I will explain that. Okay, you will see. Yeah, and then eventually go to the API. You, as I said, you use the hardware HWH, the hardware header file information. The API will read this, and this one will link with the block design. when you want to generate the IP, okay, and then you generate the HWH file, and the HWH file will be read by the API, the Ipython API. That's how you link them all together. Okay, I will explain this part in the later slides. Okay. Another one you want to know, allocate. Okay, allocate is an XL link. Okay, so it's basically they are it's the same thing. Yeah. So when the Pfpga kernel function want to transfer data back and forth between the PSI DDR memory, first thing you need to allocate. Okay, the PSI, you have to allocate the buffer in the DDR memory. Okay, and the pointer or the buffer address has to communicate to the DMA engine. The buffer address, the address has to program to the DMA engine, tell the DMA where you can start to access this data. Okay, so this API, it does the memory allocation, so it makes sure it's a physically continuous memory buffer object. It's quite important. So that's why allocate, they cannot simply call the OS memory allocate. Because you directly call the OS memory allocate, it doesn't guarantee the memory allocate are contiguous memory. Okay, so for this one, it has to allocate a big chunk of a memory from the OS, and then it manages all the memory allocation or memory management by its own. Only doing that, that can guarantee when you request the memory buffer, and there will be continuous memory. Yeah. So that's why you cannot directly use the OS allocate. If you use allocate, all those memory are, not continuous. It's if you use allocate, it is continuous. However, it's continuous in virtual address space. Okay, but physical address space is a scatter. It's scattered. However, for the DMA to transfer data, it transfers to the physical address. So that's why it needs a physically continuous memory buffer. Yeah. Otherwise, the DMA engine, you have many descriptor for each. For example, if the memory you allocate is scattered in these 3 sections, how do you let the DMA to transfer all the data together? Then you have a program 3 descriptor to transfer each one in sequence. Now that's a lot of overhead, a lot of communication. Yeah. So that's why you allocate the API. Yeah. Okay. So far it's okay. I'm talking about a lot of the OS. It's very basic the OS concept.
蔡依林 faces in.
Okay, good.
Okay, Professor La, I have another question. Is like the points that we need to allocate the contiguous address is that because DMA has the less overhead to load the address which is continuous than the address ladder is not contiguous, so we can have a less overhead. Is that the point of that?
Oh yeah. First, the DMA. First, you know, the DMA only use the physical address. That's important. Okay, and it can support fragmented or scattered memory, but the DMA must have a capability to have for example, you have a region 1 or region 2 and region 3. Okay, then you need to have a descriptor, 3 descriptor. Okay, descriptor 1, descriptor 2, and descriptor 3. And each one, this one point to the region 1, and this point to the region 2, this point to the region 3. Okay, then you need to use a DMA with this kind of capability in order to deal with the scattered memory buffers. But in the PYNQ, the DMA engine uses very simple. It can only take one memory, one descriptor. Yeah. So that's why you have one physical. Otherwise, you have to break down the 3 transfer into 3 DMA transfer. Okay? Because each DMA could only transfer 1 region. Yeah, and 3 transfer takes out a lot of overhead. When the data transfer, it has to let the driver know, okay, I transfer the first region. And then the driver program the second region, and then it starts transfer the second. And second down, then it starts transfer the third one. So it has a lot of synchronization overhead. It will be very, very slow. You will find out transfer data is fast, but the synchronization takes up a lot of time. Yeah. So for the efficiency of data movement, we really like to have a physical continuous. Otherwise, they use this kind of DMA can take multiple descriptors. Yeah, but this multiple descriptor is not the one used in the PYNQ anyway. Yeah, remember the driver and the IP has to bind together. Yeah. Okay. It's important. For example, for PYNQ, if you know all the know-hows, you can develop your own PYNQ, improve the PYNQ framework. For example, I decide use a better. For example, I like to use this kind of DMA, and you develop its own drivers. Then it provides much more flexibility. Yeah. Okay, and for example, PYNQ, the framework doesn't support out-of-order operation like XRT, OpenShield XRT. That support out-of-order. But PYNQ is a very simple one. It doesn't support out-of-order. So the host program and the kernel function, when it's run as a whole system, is not quite efficient. Because we know the out-of-order can improve the system utilization or efficiency. Yeah, and PYNQ is too simple, so you cannot run multi-thread or multi-kernel functions, which may have out-of-order operations. And PYNQ doesn't support it. So PYNQ, if you're really interested in embedded programming, you can take a PYNQ as an example to develop much advanced, or try to provide all the XRT functions into the PYNQ. They will be very interesting project. Yeah. Okay, so let's talk about the lab. Okay, let's start from the lab 1 multiplication, and lab 2. So in the level 1 and 2, introduce all the 3 critical interface between the PS and the PL side. Okay, let's start from the first one, the multiplication. Okay, so that's a very simple code. Okay, it just does a multiplication. Okay, and that's the interface. You can see here, you have a in1, you have a in2. Okay, and the in1 and in2 comes in, it does the multiplication, and the multiplication result coming back, you put into the out. Okay, so that's the kernel function, and the PSI, and the PSI, then we need to provide the in1 and in2, and the result we will read it back. Okay, and all this is specified that we use AXI light. The interface we're using AXI light. That means for the PS side, we will use the general purpose port 0 and generate an AXI light transaction to write to the in1 and in2 and read the data out. Okay, you will recall all the previous slides. Yeah. So in here we use the pragma. Yeah, specify the out using the XI light, in1 into XI light. Yeah. Okay, then let's see the next one. Okay. So when you compile this function, let's see. Okay, then when you do the synthesis, HLS synthesis, and then you export IP, then you got this IP. That's your kernel function. Okay, and then you get into the block design. Integrate this IP with the rest of infrastructure component. Okay. And we look at this IP, it has the only AXI light interface. As I said in the previous, we only use the AXI light. Okay. And how do you interconnect them? Okay, first that's the PS side. Okay. And that's the system reset. So you don't care these two. Okay. And here you use the AXI interconnect. Okay, that's a general IP because what it does is bridge the frequency. Because this side, the PSI frequency and the frequency you are running here may be different. So it will does the frequency translation. It will does the bit width or bus width. Okay, in here, that's a 32 bit. The general purpose port, we see the 32-bit, and it happened, this is 32-bit too. But in some cases, the bit width may be different. For example, for the high performance port, there's 64-bit. And here you may use a 32-bit. So you use this IP to bridge the bus width difference. And it also does protocol translation. For example, in here, there's a pure AXI master interface coming out the PS side. But in here, there's the AXI light. The protocol are different. So you also use this IP doing these things. Use this IP doing these things. Three things: frequency translation, bus width translation, and protocol translation. Okay, so definitely you use it. So in here, let's look into the connection. The general purpose port coming out here. Okay, and then it translate, does all these things and coming out here to the XI light of this IP. Okay, you connect them, and then coming out, then you program the address editor for the PS side. Okay, you specify in here you specify what address will be going direct to here. Because CPU could program all kind of address coming out of the general purpose port, master port, can be any address. Okay, some of the, if and only the address falling into this range, the cycle will go into here. Okay, so use the configuration from the block design. You configure, and I think that this address is automatically generated by the tool. Yeah, I believe above 1 gigabyte, below 1 gigabyte is a system memory. That's an onboard DDR. Okay, right now the system only 112 megabyte, and about 1 gigabyte it goes to the I/O region. Okay, so if the address below 1 gigabyte, it just goes to its internal DDR, and above 1 gigabyte, then it goes to the I/O, go to the peer side. Okay, and then on peer side, what address range should forward the cycle going to this IP? Then you specify in here. Okay, this address, remember this address, okay? Because this will be used in the upper driver. For driver to access this one, you have to use this address range. But how those address range get to know by the driver or API going through here. Okay, so the after you do the block design, it will explore this metadata file and the HWH file. Okay, and in here, that's how you configure. Let's look at, and in here, see this AXI filter, the base address is appear in the block design address editor, right? Okay, and inside this range, how the kernel function argument arranged. Okay, how do you access each argument? It's defined by the HWH in here. Okay, generate address map document here. Let's look at here. Okay, the below the address, the below 16 bytes is the for block level protocol. The block level control, they control the whole module. Okay, and for this module, it doesn't have any protocol. It's a pure combinational module. Okay, no control mechanism. So there is nothing defined here. Okay, and later we will see if you use a different block level protocol, then you have some control here. Okay, and we will see in next example. And let's see here. Okay, if you want to program, remember you have a register in1, register in2, and the output here. Okay, and that's your argument here. Okay, so the argument, the offset for each argument is by the order appear in the argument list. So starting from 1, 0 is defined in1 because the in1 is the first argument. Okay, it defined 8 bytes. Okay, and then this address. Okay, remember this address. Then in the host program, you're going to use this address to program into the in1 register. Okay. And that's the in2. And then the next one is out. Okay, the register out at the 2, 0. And the out, it uses a protocol using the AP valid. That's a default protocol for output. So this status register is important because you don't know whether the output is valid until the AP value asserted. If you read the AP value bit is 1, then you can read this data content. But since this circuit is a pure combinational, that means whenever you apply 1 and 2, the out valid almost instantaneously, immediately. Okay, so in our code, then we don't really check this. Otherwise, before you are able to use the output value, then you have to check whether it's valid. Yeah, but since it's a pure combinational logic, then yeah, the output just appear immediately. Okay, and then let's come to how to you access the kernel function by, from the host. Okay, from the host, you have first open the overlay, and MMIO, it doesn't explicitly to import MMIO because the MMIO is embedded in the overlay. Okay, so this and then in the overlay, basically that's the image file, the bitstream image. Okay, and inside you may have a multiple kernel functions. You have a multiple kernel function, and the kernel function we are interested is this one, and this is the top function name. Okay, then you get this IP, and then you access the IP. First, remember we want to program the two operand. One is a 1 0 and one is that's the in 1, and that's the in 2. Okay, the 1 0 and 1 8. Yeah, look at the HWH file. You know that's the address you can access in 1 and in 2. Yeah, and then you get the output, and then you read the output at 2 0. Okay, yeah. So right now you got the whole idea. That's a very, very simple one, okay? So let's refresh, okay? You have your code written in this way, and you specify this argument is xILite. And then when you generate IP and you block design, connect them together. When you connect them together, you have specify how to access this xILite register, this address. Yeah, it's most likely the tool assign this address for you, but you have to remember this address. And then actually you don't remember, you don't need to remember because API read the HWH file, then yeah, he knows that. Yeah. And then how do you access each argument? Then you look into the HWH file, then you will know the address, the offset address. And then write the code directly access those offset address to access the xILite register. Okay, yeah. So you understand. Then let's look at the next example, xi master. Okay. So this FIR11 example. Okay. So this FIR, we don't really get into the detail how to develop the FIR11 HLS code because that's another main purpose here that we will introduce in the HLS sessions. Okay, so this basically you have an input string. Okay, you have an output string. Okay, and then that's the FIR. So you have a type register, type parameters. Okay, it's defined by an array here. Okay, and then you have the data transfer length, the input length. You define it here. Okay, you have those arguments. Okay, and then in here you can specify as one for the XI master. First, you use the XI light to specify XI master. You need to XI master configuration. What kind of thing you need to program? For example, like the base address. Okay, what address in the DDR memory that you want to access? Okay, and length, for example, those information that the XI master need to know. So you need to create an XI light so that you can program into it. And for the two argument, that's a pointer. Actually, it's a memory pointer to the memory buffers. Okay, it's specified using the XI master cycle. And then you have a FIFO depth. Okay. And then the coefficient, remember the coefficient here using the XI light. So coefficient, you use the CPU to program into it. And the transfer length using XI light to program into it. Okay, so you use this is called the directive. Okay, the directive is specified in a separate file called directive.tcode. If you use the GUI, the VTs, HLS, use this one, then you can use the GUI to set those directive. And you set using the GUI, you can have two options. One is make the inline. That means it will become Ppragma inside your source code. Or you want to use the directive that will pull all those Ppragmas or directives in a separate file called directive.tcode file. And in this example, it use the directive file. So use a set directive. So for each of the directive, it has a corresponding Ppragma statement. The Ppragma is embedded in the C source code. Okay, so why we use the two method? I should have a blank PPT slide so that I can explain more. Yeah. Okay. If you use the directive put into a separate file, that means you separate your source code and the optimization separately. It gives you the advantage that you have the same source code, but you supply with a different directive. It gives you a different result, right? Different target optimization targets. Yeah. But however, these two things are separate: the source file and directive file. And these two files, when you doing the transfer, when you hand over to somebody else, the two files doesn't link together. Okay. So people get your the GitHub open source code that they may not link together, may not duplicate the same result. But if you are inline into your source code, then everybody get the source code compile, get the same result. Yeah. So depending on your application scenarios, you decide whether you use a directive or use an inline pragma. Okay. So in this example, using the directive. So all the directive is in separate file, separate from the source code. Okay. Then that's wait. What happened? Why is it appearing here? What happened? Why write down is appearing this slide? Okay. Wow, it's all messed up. This slide. Okay, let's look at here. FIR XI master. Okay, so this one is our kernel IP. Okay, and we have a XI lite and we have the XI master. Again, in order to connect to the PS side, this is a PS side. Okay, and we use a two interconnect. Okay, for this interconnect, basically is provide the XI lite. This provide the XI lite. And this one is for the XI master transfer. Okay, remember here, there's a 64-bit. And this here is 32-bit. So that's why, and frequency may run differently. So this, although this is a XI master, and this port is a XI master, it simply cannot directly connect. It need to use this interconnect. Okay, this one is obvious because it does XI master to XI lite protocol translation. So that's how you connect to the whole system. So here, in here, we notice for the XI master, you have this configuration address space here. And you have also another XI lite. For example, you need to program the coefficient and length, right? Yeah, so you need another address range. Yeah. So in here, that's the for you to do the host programming to control the kernel function, you need to look into the HWH file. Okay, and in here, look at here. In here, you need to have a block level protocol. Okay, so in here that you use the AP start, and right now you probably don't understand those signals. In the later the I/O kernel I/O interface, we will explain in greater detail. But for now, since the FIR is not as simple like a multiplication, that's you don't use any block level protocol because it is pure combinational logic. So you don't need a protocol to control these kernel functions. But for FIR, you do need to tell them when to start. Okay, it doesn't run when reset. Okay, it only runs when you tell the kernel function to run. Because before you can run the kernel function, you have to prepare the input file. You have to prepare everything before you can call the FIR start. So you need certain protocol to initiate this kernel function. So that's the protocol you use. So it defines the AP start and AP done. Okay. So you want this kernel function or FIR filter to start running, you program this bit. When the FIR finish all the input data, then you will assert AP done. You can read this register B, then you know FIR is done. The function is done. Okay, so that's how the host program and the kernel function communicate. Yeah, so for now, you just remember these two. And then let's look at the starting from 1-0. Yeah, you have an input. Remember the input, you need to specify the input buffer address. Okay, that's where you tell the XI master where you can get the input data buffer address. And the output will save to this address. That's the output buffer address. And that's the transfer length. And that here, that's how you program the coefficient. And actually, you only need to have 11 coefficient, but it has to be 4 by 9, so it becomes 12. And starting from 4-0. Okay, you program that much of coefficient. And then let's look at the source code or the host code. Okay, in the host code, first you open the overlay, you get this kernel function out, and then in here you try to or the data is saved in data file. Okay, and in here you simply try to find out how many samples here. Okay, then you have a number of samples, then you need to create the input buffer and the output buffer based on number of samples. Each sample is 32 bits, so you allocate the memory buffer, in buffer and out buffer. And in here, you try to fill in the input buffer. Okay. And there's a coefficient, and you try to program the coefficient. In here, you program the coefficient. So which address you program from 4-0? Okay, that's defined in the HWH. This is defined in the HWH file. So you program the coefficient, and then you program the A0. Why is the A0? A0 is the transfer length, right? If you remember, you program the transfer length, and then you program the address 1-0. That's the input buffer address, and 1-8 output buffer address. And then you tell it start 00 and B01. B01 is the AP start. Okay, so AP start must be the last. Before that, you have to program all the necessary configuration. For example, if you start program the AP start, if we move over up here, before you program the input buffer address, you will run into trouble, right? Because once you start AP start, it start fetching data from system memory. But at that time, you haven't programmed the input buffer address. So you will fetch the random address. And you will start writing into the output buffer. But you didn't specify the output buffer address. So there's gonna be a random address. So data will write to the random address in the system memory and could be in the kernel section. Then your system maybe just crash. Okay, the whole embedded system doesn't have any protection mechanism. It doesn't have an MNU to guard you from mess up the system memory. So you simply write to the random address, then maybe just write to the kernel function. Remember, those DMA address access directly to the system memory. It doesn't go through OS. So OS has no way to prevent any malicious code or any access. There's simply no hardware mechanism to prevent that. Yeah. So when you do the embedded programming, there is no protection whatsoever. So you have to do it very carefully. Otherwise, system simply crash. Yeah. So important for doing embedded system programming, you have to know the hardware behavior in very detail. And all the sequence order is very, very important. Yeah. So that's a very basic embedded system design. Yeah. Okay, let's example the AXI string. So another example using the same code. However, we want the input and output using different way to access system memory. In here, we are using the string. Okay, this is how you define. Okay, you set the transfer length, coefficient, they are all xi like. So this two is the same as before. However, the input and output right now is not using xi master, it's using xis stream. Yeah. So let's see here. However, the PSP interface doesn't have string interface. Okay, so you need a DMA, a particular IP, to translate stream interface to XI master. So this is these two IP coming into place, this IP and this IP. So you have the same two interconnect. That's for the XI Lite interconnect. That's for the master access interconnect. And so for support the stream, you need to use another IP. That's basically the stream to XI master conversion. You have to use exactly the same IP. You cannot use any other IP because, as I explained, that those IP tied to the driver code, tied to the API in the PYNQ framework. Yeah, and that PYNQ framework is designed target using these two DMA conversion IP. So you have to use exactly the same one. Yeah. So so for the kernel function, it's a streaming in and streaming out. And streaming in, you convert from the master cycle, master going here to this DMA, and then it convert XI master to stream interface. And the streaming out, you use another IP, convert the XI stream to XI master, and then if at the late stage, it's to the PSP XI high performance pole interface. Okay. Again, you need to specify the address range. In here, we have a 2 DMA engine here. Okay, that's a XIM to string. That's string to memory. Okay, and then so this DMA, the working range is from 0 to 512 because the system memory, as I say, is a 112 megabyte system memory. So this DMA on the master side, the address range is from 0 to 512. Okay, and you need to program this 2 DMA engine So there's a XI-DMA in and XI-DMA out. That's the two DMA engine we'll be using. And you want to program them, then you use this address to program. And for the kernel function, you have like a transfer length and coefficient. Yeah, and you use this address range to program. Okay, so in here, so that's for the kernel function. Yeah, yeah, we have before here. That's the block level protocol. Yeah, so we use the same thing. We use the AP start and AP down. Yeah, to control the block. And in here, there's a transfer length and coefficient. Okay. And for the two DMA IP, actually you need to program the source address. Okay, that's a 64-bit source address and transfer length. Yeah. So the two DMA, one is the XI-DMA in. So you need to program this base address with offset 18, and the length is 28. Okay, so for the output stream, okay, actually using the same DMA IP, yeah, and there's a full base address here. Then you also use the that's a S to M string to system memory for output. So you want to program the memory base address as from 48 and the length using 58. Okay, but this detail, you don't see this detail because API handle it. API already handle it, so you don't actually program it. So when you look at the code, this is the code. This part all the same, okay? The same and the type program, yeah. So you allocate the in buffer and out buffer, yeah, here. Okay, look at here. So you need to program kernel. Two parameters you need to program. One is the transfer length you program in here. And also you need to program the coefficient. Okay. And the two DMA engine here, you simply tell him the input buffer, 0 and output buffer. Yeah. And this information already tell you the starting address and length about it. So inside the API, this 2DMA API, it will program the DMA engine automatically. So you don't actually program that DMA engine. This API handle it for you. Yeah. So if you are interested that you can really dig into the PYNQ open source code, you try to find out those DMA IP, and then look at the detailed code. You will see, you will access those offset address in order to program the starting address and transfer length. Okay, yeah, so that's explaining here. Okay, so that's the PYNQ lab 1 and lab 2. Yes, yeah. So there's a very simple question here you can try to answer. So given the block design with this information, then in the this JSON file what do you expect for these two numbers, A and B? Can you try to answer? This is in block design, and this is the output file, and this output file will be used by the Python API code. So can I see anybody answer that? Okay, DBC 0. Yeah, okay. Yeah, so basically just these two numbers coming here. Okay, good. Yeah, very simple one. Okay. And the second question, okay, if you have a FIR, and then can you write the code to start the kernel execution?
Excuse me, teacher, you haven't turned your page.
Oh, okay. Wait. Okay, yeah. Okay, right, 0, 0, and B 0, so it will be 0, 1, right? Okay, good. Yeah. So it's a Yanfu, it's Jiafu's brother. Why he knows all the answers? Okay. Yeah. Okay, question 3. Okay, let's say that that's actually I explained. Can I move this code, this piece of statement, move up here? Yes, no question. Yeah. So I explained that you could not start executing kernel before you configure everything down. Otherwise, you simply crash your system. Yeah. Okay. So the code sequence is very, very important. Yeah. Okay. So this concludes the PYNQ. Yeah. Hopefully, it give you the whole pictures. Oh, Yilin. Yeah, you have a question. Yeah.
Okay, yes. I just realized that for XI Lite, the bits is for 32 bits. And what if our hardware design is not 32 bits? For example, if we are doing the hardware for audio, then 24 bits would be enough. And so, do we just simply specify that for address 0 to address 4, the first 24 bits is data 1, and the 32 to 25 bits is data 2, and the other 16 bits is in the address 4 to address 8, something like that?
You are talking about audio data, right?
Yes, because for audio data, we don't need 32 bits for data. 24 bits
Yeah,
would be enough. Yeah.
Okay. For that, okay, remember for XI Lite, we use for configuration first, or small amount of data. Okay, for audio, video, those are streaming data. Okay, so you should use the DMA. So suppose you have a audio file, and you either put into the system memory, load into the DDR memory. Okay, and you say this is 24 bit. The native data is only 24 bit. Okay, there are several ways to do that. Okay, or if you do the real time, that's audio is streaming in. Suppose you have a microphone. Okay, and then you have the FPGA. My phone come in, then you may have a AD converter, and the output is 24 bits, for example. Okay, or either the two are quite similar. Okay, for this one, that's in memory. Then you may use the DMA engine from MM to S, right? From memory to S. Yeah, and the memory is 32 bits. When the bus interface actually right now is 64 bits, high performance transport, 64 bits. Okay, so it depends on how you populate your streaming audio data. You may waste your memory. Are you talking? You can all hear me?
Yes, I can hear.
Yeah. Okay. Yeah. So depend on how you store your audio data in the system memory. Okay, and then you can use a 32-bit memory, however, only save 24 bits. Okay,
Yes.
that make it easy that the 32-bit, and then when you comes in, you drop 8 bits. You only get the lowest 24 bit to use it. That's one way you can use that. Or you want to fully pack the 24 bits. In that case, however, when you access the DRAM, you can only access in 64-bit quantity at a time. Then you need to manipulate the each 24-bit thread out. You need to do something processing. So before the MM to S, then you may need to have a certain logic to handle the bandwidth difference. For example, you read the 64-bit DRAM, and then it may not be the multiple 24-bit, then you need to truncate certain bits and save it for next 64-bit data. So you need to do some kind of data assembly here, logic. Yeah. At the end, these two all coming out 24-bit streaming data. So you can use the same kernel function and using the streaming to do the processing. It's better that you design a kernel using the streaming so that you can test it through this path. And in the future use, you want to have a real device connect to microphone and then streaming in with 24-bit. The same kernel can handle these two cases. So it's better design this way. And then you need to bridge all the difference in front of here.
Yeah. So does it mean that if we are designing another bits which is not 32 bits, we need to design another part of the hardware to translate from the 32 bits to the bits we want?
Yeah, you can do whatever. Like the Xilinx provide a VDMA IP. There's this IP, you can look up the VDMA, and VDMA is very flexible. Basically, it's from memory to stream. Okay, and the memory could be any bandwidth, and the stream any bandwidth. So it does all the dirty work here for you. Otherwise, you have to design quite. Yeah, it's quite headache to handle.
It's a really good news. We have an IP.
Yeah. It's very popular for video, like RGB, 8-bit. This is 24-bit, and audio could be 24-bit audio, right?
Yeah, exactly.
Yeah. So it's quite common in image or audio applications. So that's the need, quite common need. Yeah.
I see. Thank you, Professor Lai.
Yeah. Okay. Yeah. Okay. Question 3. Yeah. So we will end of PYNQ. Any more question?